What are the odds that two stars would explode into naked-eye visibility? That two massive earthquakes would tear through Venezuelan bedrock? And that the infamous interstellar object 3I Atlas would get sideswiped by a solar storm, all within 72 hours? If this were a movie script, editors would reject it as too coincidental to believe. But this is reality. And reality just delivered the most synchronized cosmic performance in modern astronomical history. After what just happened, even the most rational minds are starting to wonder if we're witnessing something far stranger than chance. Tonight, we'll dissect each event with surgical precision, examine the science behind stellar tantrums and planetary convulsions, then venture into the uncomfortable territory where coincidence meets pattern recognition. Stay with me until the end, because what we discover about September 2025 might challenge everything we thought we knew about what's really happening up there. Part 1. An insane chain of events. Two stars explode. Two massive earthquakes rupture the ground beneath Venezuela. And an interstellar visitor gets sideswiped by a coronal mass ejection. All within days of each other in late September 2025. If you're starting to feel like the universe is trying to tell us something, you're not alone. Let's map this cosmic collision of events with precision. On September 23rd, astronomers detected V1935 Centauri, a nova that erupted in the southern constellation Centaurus, brightening to naked-eye visibility at magnitude 5.8. Within days, another stellar explosion announced itself, V794 Sagittari, blazing forth in the Archer constellation at magnitude 6.2. Two stars, both suddenly visible to anyone willing to step outside and look up. Meanwhile, 7,000 miles away from the nearest observatory, the Earth itself was making headlines. At 22:21 UTC on September 24th, a magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mene Grande in Venezuela's Zulia state. The tremor, originating just 7.8 kilometers below the surface, sent shockwaves across both Venezuela and Colombia. But nature wasn't finished. Hours later, at 03:51 UTC on September 25th, a second quake, magnitude 6.3, ruptured the same region, this time from 14 kilometers down. Twin stars, twin quakes, and overhead, invisible to the naked eye but tracked by satellites, something else was unfolding. Solar weather forecasters at NOAA's Space Weather Prediction Center were monitoring coronal mass ejections, billion-ton clouds of magnetized plasma hurled from the sun at speeds exceeding 1,000,000 miles per hour. Their computer models suggested these solar storms were crossing paths with something unprecedented. 3I Atlas, the third confirmed interstellar visitor to our solar system. Here's where the timeline becomes almost theatrical in its synchronicity. The nova discoveries and Venezuelan earthquakes clustered around September 23rd through 25th. CME forecast models showed peak activity during the same window, and 3I Atlas, discovered just 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, was navigating the inner solar system during what may be the most active period of solar cycle 25. The geography of these events spans scales that challenge human intuition. The novae erupted in Centaurus and Sagittarius, constellations visible primarily from Earth's southern hemisphere, their light having traveled thousands of years to reach us precisely during this remarkable week. The earthquakes struck near Mene Grande in northwest Venezuela, in a tectonically complex region where the Caribbean and South American plates grind against each other. The coronal mass ejection propagated through the inner heliosphere, a volume of space larger than Jupiter's orbit. And 3I Atlas? It was crossing the ecliptic plane, the imaginary disk where most planetary action takes place, threading between Mars and the Sun. We're not claiming a causal chain here. That would be premature, possibly reckless. What we're doing is mapping the cluster, documenting the convergence, and preparing to weigh mainstream scientific explanations against more adventurous hypotheses. The U.S. Geological Survey maintains no demonstrated connection between space weather and earthquake activity. Solar physicists would tell you that coronal mass ejections are routine features of an active sun. Stellar astronomers see novae as predictable, if unpredictable, consequences of binary star evolution. But here's what makes this week genuinely unique in modern astronomical history. 3I Atlas represents only the third confirmed interstellar object ever detected, following Oumuamua in 2017 and 2I Borisov in 2019. More intriguingly, this is the first time we may witness an interstellar visitor subjected to intense solar weather near solar maximum. We have precedent for what CMIs can do to solar system comets. In 2007, the European Space Agency's stereo satellites filmed a coronal mass ejection, literally tearing the ion tail off Comet Encke, a disconnection event that demonstrated the violent reality of space weather interactions. The stakes for the coming months extend far beyond academic curiosity. 3I Atlas is scheduled for a Mars flyby on October 3rd, passing within 0.19 astronomical units, roughly 28 million kilometers of the red planet. Mars orbiters, including ESA's ExoMars and NASA's Mars Reconnaissance Orbiter, are preparing opportunistic observations that could resolve details of the interstellar visitor's nucleus and coma at unprecedented resolution by late October. Specifically, on October 29th, 3I Atlas reaches perihelion, its closest approach to our Sun, at 136 astronomical units. Still outside Earth's orbit, but close enough for ground-based telescopes to study its composition and behavior in real time. The viewing geometry becomes even more favorable by December 19th, when 3I Atlas makes its closest approach to Earth at 1.8 astronomical units. For comparison, that's closer than Mars at its most distant, offering months of observation opportunities for both professional observatories and amateur astronomers equipped with modest telescopes. This convergence arrives during a season when space weather traditionally intensifies. The autumn equinox triggers what space physicists call the Russell-McFerran effect, a geometric quirk in Earth's magnetic field orientation that amplifies geomagnetic coupling with solar wind disturbances. September through November historically produce some of the year's most spectacular auroral displays and most significant space weather impacts on technology. Our promise to you is this: we'll deliver both clean scientific explanations and bold what-if scenarios, but we'll label each clearly. You deserve to know what's observationally confirmed versus what's scientifically speculative versus what's frankly imaginative. The data matters, the wonder matters, and sometimes the most honest thing science can say is, we don't know yet, but we're watching. Consider this question as we dive deeper. If coronal mass ejections can strip the tails from comets that have orbited our Sun for millennia, what might they do to an object that spent millions of years traveling between the stars, carrying ice and dust formed in an entirely different stellar system? We're about to find out. Next, we'll examine those sudden stellar explosions, the twin novae that lit up southern skies just as Earth's crust began to shake. Part 2. The twin novae, sudden southern sky explosions. In the pre-dawn hours of September 23, 2025, amateur astronomer John Sench was doing what he's done for decades, scanning the southern skies from his observatory in Chatsworth Island, New South Wales, hunting for stellar explosions. What he found that morning would soon grab the attention of gamma-ray satellites and X-ray telescopes across the solar system. V1935. Centauri announced itself not with fanfare, but with photons. Sench's initial detection showed a star where no star had been bright enough to notice before, sitting in the constellation Centaurus at magnitude 5.8, just bright enough for keen-eyed observers in dark locations to spot without binoculars. But this was no ordinary brightening. Within hours of Sench's discovery report reaching the Central Bureau for Astronomical Telegrams, space-based observatories began detecting something extraordinary. NASA's Fermi Gamma Ray Space Telescope triggered on high-energy photons streaming from the nova's direction. The Swift Observatory, designed to catch gamma-ray bursts, swiveled its X-ray telescope toward Centaurus and began recording hard X-ray emissions, signatures of violent particle acceleration in the nova's expanding shockwave. These weren't just pretty lights for backyard stargazers. This was evidence of physics operating at extremes. Electrons and protons accelerated to near-light speeds, magnetic fields twisted into knots, temperatures soaring into the millions of degrees. But V1935 Centauri wasn't finished making headlines. Just days later, Sench struck again. Or rather, the cosmos did. V79994 Sagittari erupted in the neighboring constellation Sagittarius, reaching magnitude 6.2 at discovery. Two stellar explosions, both credited to the same observer, both bright enough for small telescopes or binoculars, both occurring within the same remarkable week. Here's why this pair caught professional astronomers off guard. While novae aren't exceptionally rare, perhaps 10 to 12 occur in our galaxy each year, having two reach near naked-eye brightness within days is genuinely uncommon. The last time observers enjoyed two bright novae simultaneously was during the summer of 2023. And before that, you'd have to reach back several years to find comparable displays. The physics behind these eruptions tells a story of stellar cannibalism played out over cosmic time. Each nova begins with a white dwarf, the dense, hot core of a dead star, roughly the size of Earth, but with the mass of our Sun. This stellar remnant sits in orbit with a normal star, gradually stealing hydrogen from its companion's outer atmosphere. For years, centuries, or millennia, gas accumulates on the white dwarf's surface, growing denser and hotter under the immense gravitational compression. Eventually, temperature and pressure reach a critical threshold. The accumulated hydrogen undergoes runaway thermonuclear fusion, not the controlled burning that powers living stars, but an explosive conflagration that can brighten the binary system by factors of 10,000 or more. The explosion doesn't destroy the white dwarf. Instead, it blows away the surface layer, returning the system to its patient process of accumulation. Some novae recur on predictable timescales, erupting every few decades. Others may wait thousands of years between outbursts. V1935. Centauri's gamma-ray and hard X-ray signatures reveal the nova's most violent aspects. When the thermonuclear explosion launches material outward at speeds of thousands of km/s, it creates shocks that accelerate particles to enormous energies. These relativistic particles interact with magnetic fields and surrounding matter, producing the high-energy photons that triggered Fermi and Swift. It's the same physics that operates in supernova remnants and active galactic nuclei. Cosmic particle accelerators that turn ordinary matter into high-energy radiation. For observers in Earth's southern hemisphere, both novae occupy prime viewing territory. V1935 Centauri sits well south of the celestial equator, making it a challenging target for northern observers who must wait for it to rise above their southern horizon. V7994 Sagittari, located in the Archer constellation, presents similarly southern viewing geometry. Appearing low in the south for mid-northern latitude observers, but riding high in the sky for anyone south of the equator. The discovery process itself reveals the collaborative nature of modern, transient astronomy. Sencha's initial observations, reported through the International Astronomical Union's Central Bureau, triggered a cascade of follow-up observations. Circular number 5611 confirmed V1935 Centauri's detection, while 5612 documented V794 Sagittari. Within days, observatories around the world were obtaining photometry, precise brightness measurements, and spectroscopy that revealed the characteristic emission lines of hydrogen, helium, and heavier elements in the expanding nova shells. Amateur astronomers play crucial roles in nova science through organizations like the American Association of Variable Star Observers. Their nightly monitoring provides the temporal resolution that reveals how nova light curves evolve. The complex patterns of brightening, plateau phases, and gradual decline that contain clues about the explosion physics and the binary system's properties. Professional telescopes can't monitor every nova continuously, but dedicated amateurs can track brightness changes night after night, contributing data that shapes our understanding of these stellar explosions. The naming convention often confuses newcomers to astronomy. V1935 Centauri received its designation as the 1,735th variable star officially named in the Centaurus constellation, while V7994 Sagittari became the 7,094th in Sagittarius. These permanent names replace the temporary designations assigned at discovery, which can sometimes make the timeline appear confusing when later discovered objects receive earlier numbers due to administrative processing delays. Both novae are expected to fade over the coming weeks and months, following the typical nova decline that can span months to years. However, their evolution may include surprises. Some novae develop dust formation episodes weeks after eruption, temporarily dimming as newly formed dust grains absorb and scatter the nova's light. Others show complex, multi-peaked light curves as different physical processes dominate at different times. The question that space weather enthusiasts can't help asking is whether these stellar explosions, occurring during the same week as significant geomagnetic activity, represent more than coincidence. The mainstream astronomical answer is clear. Novae in neighboring constellations, located thousands of light-years from Earth, pose no direct threat to our planet and exert no measurable influence on terrestrial phenomena. The energy from these explosions, while enormous by human standards, dissipates across the vast distances of interstellar space, arriving at Earth as a gentle increase in photons, beautiful to observe, harmless to experience. Yet the timing feels remarkable. Twin stellar explosions during a week of twin earthquakes, with an interstellar visitor threading through active solar weather. Perhaps the most honest response is to acknowledge both the science and the synchronicity, to appreciate the physics while remaining open to the possibility that our universe occasionally arranges itself in ways that stretch coincidence toward something approaching poetry. Meanwhile, 7,000 miles from any observatory capable of detecting these stellar fireworks, the solid Earth beneath Venezuela was about to demonstrate that explosions weren't limited to distant suns. Part 3. The Venezuelan Quakes. At precisely 22 hours, 21 minutes, and 55 seconds Coordinated Universal Time on September 24th, the Earth's crust beneath Venezuela's Zulia state released energy equivalent to several nuclear weapons. The magnitude 6.2 earthquake struck 24 kilometers east-northeast of Mene Grande, originating from a relatively shallow depth of 7.8 kilometers, close enough to the surface to shake buildings across two nations. The seismic waves propagated outward at roughly 6 kilometers through the rock, reaching populated areas within seconds of the rupture. From Maracaibo to Caracas, From Colombian border towns to Caribbean coastal cities, millions of people felt the ground sway beneath their feet. Social media erupted with videos of swinging chandeliers, rattling windows, and residents evacuating buildings as emergency protocols kicked into action across the region. But the Earth wasn't finished. Just 1 to 2 hours later, at 03 hours, 51 minutes and 39 seconds UTC on September 25th, a second major rupture struck virtually the same location. This time, the magnitude 6.3 earthquake originated from 14-kilometer depth, deeper than its predecessor, but still shallow enough to generate intense surface shaking. The epicenter sat approximately 27 to 28 kilometer east-northeast of Mena Grande, overlapping the first event's rupture zone. To understand why these twin quakes matter, we need to grasp the logarithmic nature of earthquake magnitude scales. A magnitude 6.3 earthquake releases approximately twice the energy of a magnitude 6.2 event. Combined, these two ruptures produced energy equivalent to a single magnitude 6.4 to 6.5 earthquake, a significant release, even by global standards. The September 24th and 25th events represented the largest seismic activity in the region since the magnitude 7.8 Kamchatka earthquake on September 18th, placing Venezuela's twin quakes among the most notable global seismic events of late September 2025. The aftershock sequence provided its own drama. A magnitude 5.8 earthquake struck the same region later on September 25th UTC, following the typical Omori decay pattern that seismologists expect after major ruptures. While 5.8 might sound modest compared to the main shocks, it's still large enough to cause additional damage and maintain anxiety levels among regional populations already stressed by two major events. Regional tectonics explain why this area generates such powerful earthquakes. The Maracaibo Basin sits within a complex zone where the Caribbean plate grinds against the South American plate, creating a network of fault systems, including the Bocano Fault System and the Urumaco-Santa Marta fault trends. These geological boundaries have been accumulating stress for years, decades, or centuries, storing energy that eventually must be released through sudden slip events. Earthquakes. The depth difference between the two main events, 7.8 kilometers versus 14 kilometers, matters significantly for ground shaking intensity. Shallow earthquakes typically produce stronger surface acceleration than deeper events of the same magnitude because seismic waves have less opportunity to spread out and weaken during their journey to the surface. The September 24th event's shallow depth likely contributed to the widespread reports of strong shaking across both Venezuela and Colombia. Different seismological agencies reported slightly varying magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey initially reported the first earthquake at magnitude 6.2, while the European Mediterranean Seismological Center and other international monitoring networks provided measurements ranging from 6.1 to 6.3. These differences arise from various factors: different measurement methodologies, updates as additional seismic station data becomes available, and distinctions between moment magnitude, surface wave magnitude, and body wave magnitude calculations. The human impact of these earthquakes extended far beyond seismological statistics. Evacuation orders affected thousands of residents, particularly in multi-story buildings that experienced prolonged swaying during the events. Emergency response teams mobilized across the region, conducting damage assessments and ensuring that critical infrastructure, hospitals, bridges, power plants, remained operational. While initial reports suggested relatively limited structural damage given the earthquake's magnitudes, assessment teams continued their work for days after the events, documenting both visible damage and potential longer-term structural weakening. Historically, this region has experienced significant seismic activity. The complex tectonics around Lake Maracaibo and the broader Caribbean-South American plate boundary generate regular earthquake sequences. Cosmic convergence, the universe's most synchronized spectacle, continued. Though events of this magnitude occur irregularly, the geological record reveals that major ruptures in this region can sometimes trigger additional activity on nearby fault segments, a process called stress transfer that occurs when one earthquake changes the stress field on adjacent fault systems. The timing raised questions among both professional seismologists and the public. Could additional large earthquakes follow? The statistical answer is nuanced. Aftershock sequences are expected and normal, with the largest aftershocks typically occurring within days to weeks of the main shock. However, seismologists cannot reliably predict whether an even larger earthquake might occur in the same region in the short term. The science of earthquake prediction remains elusive, despite decades of research into precursory phenomena, stress accumulation patterns, and statistical forecasting methods. International monitoring networks tracked every aftershock, building a picture of how the fault system was responding to the stress changes created by the two major ruptures. The global centroid moment tensor database began processing detailed analyses of the fault orientations, slip directions, and rupture mechanisms for both events, information that helped seismologists understand which fault segments actually moved and how the stress field changed across the broader region. For residents of Zulia State and neighboring areas, the twin earthquakes represented a stark reminder of their region's geological reality. Building codes, emergency preparedness, and community response systems all face testing during such events. The relatively moderate damage reports, given the earthquake's magnitudes, likely reflect both fortunate timing. The events occurred during hours when many people were at home rather than in potentially vulnerable workplaces, and ongoing improvements in construction standards and emergency response capabilities. The broader question that emerged from these events involves their timing relative to other phenomena occurring during the same remarkable week. Seismologists maintain that no demonstrated physical mechanism connects solar activity, space weather, or astronomical events to earthquake occurrence. The United States Geological Survey's official position emphasizes that correlations between space weather and seismic activity remain unproven, despite periodic claims in both scientific literature and popular media. Yet the human mind naturally seeks patterns, especially when dramatic events cluster in time. Twin novae, twin earthquakes, active solar weather, and an interstellar visitor threading through the inner solar system. The convergence feels significant, even if the mechanisms remain unclear. Perhaps the most scientifically honest approach is to document the timeline, understand each phenomenon independently, and remain open to discovering connections while avoiding the temptation to assume causation where only correlation appears. As aftershocks continued to rattle Venezuela's consciousness, the sun was preparing to demonstrate that Earth's immediate neighborhood could be every bit as dynamic as its solid surface. Part 4. The Sun Fires, 93 million miles above Venezuela's shaking ground. Our star was conducting its own explosive symphony. During the same days that stellar explosions lit up southern skies and earthquakes ruptured South American bedrock, the sun unleashed coronal mass ejections, billion-ton clouds of magnetized plasma that would cross paths with something unprecedented in human experience: an interstellar visitor. Coronal mass ejections, CMEs, represent some of the most powerful events in our solar system. These eruptions begin in the sun's corona, where magnetic field lines twist, tangle, and eventually snap like overstressed rubber bands. When magnetic reconnection occurs, it releases energy equivalent to billions of hydrogen bombs, accelerating plasma to speeds between 250 and 3,000 km, fast enough to traverse the Earth-Sun distance in 1 to 4 days. NASA's Space Weather Prediction Center tracks these solar storms using the WSA-Enlil model, a sophisticated computer simulation that maps how CMEs propagate through the heliosphere. The model considers solar wind speed, density, and magnetic field orientation to forecast when and where these plasma clouds will intersect spacecraft, planets, and other objects in their path. During late September 2025, Enlil forecasts showed active conditions, multiple CME events threading through the inner solar system during the same days that brought us twin novae and twin earthquakes. But here's where this story becomes historically unique. For the first time in recorded human experience, one of these solar storms was on a collision course with an object born in another star system, 3I Atlas, discovered just 2 months earlier by the Asteroid Terrestrial Impact Last Alert System, was threading through the inner heliosphere during some of Solar Cycle 25's most active conditions. The interstellar visitor, following a retrograde trajectory inclined roughly 170 to the ecliptic plane, was crossing the same region of space where Earth orbits, a prime location for encountering solar weather phenomena. We have precedent for what happens when coronal mass ejections collide with comets. The interaction isn't subtle speculation. It's documented physics, captured by spacecraft cameras and analyzed in peer-reviewed literature. In 2007, the European Space Agency's stereo satellites filmed a CME completely severing the ion tail of Comet Encke. The disconnection event, lasting several hours, demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material. Comet tails form through 2 distinct processes, each responding differently to solar influence. Dust tails curve gracefully away from the sun, pushed by radiation pressure, the gentle but persistent force of sunlight striking microscopic particles. Ion tails, by contrast, stretch straight away from our star, following magnetic field lines embedded in the solar wind. When a coronal mass ejection disrupts these magnetic connections, ion tails can disconnect entirely, drift away from the comet, and eventually dissipate, while new tails form from fresh material. The claim that 3I Atlas was sideswiped by a CME rests on model-based trajectory analysis rather than direct observation. Enlil forecasts suggested that solar storm paths would intersect the interstellar visitor's position during late September. But we must maintain transparency about uncertainty. Space weather models excel at predicting general trends, but struggle with fine details. The interaction remains a forecast, inference rather than a peer-reviewed detection. If the interaction occurred, as models suggested, we might expect several observable consequences. Increased ionization could brighten the interstellar visitor's coma, the fuzzy atmosphere of gas and dust surrounding its nucleus. Changes in ion tail morphology might appear in telescopic images, as magnetic field disruptions alter how charged particles stream away from the object. Spectroscopic observations could reveal chemical signatures, as solar energy liberates specific molecules, like CN, CO, and CO2, from the visitor's ancient ice. Amateur astronomers worldwide were positioned to document any such changes. The global network of comet observers, connected through online forums and observing organizations, maintains nightly visuals on interesting objects. Their images, when compared across time, reveal subtle changes in brightness, tail structure, and coma morphology that often escape detection by professional observatories focused on other targets. The physics of CME comet interactions involves magnetic reconnection, the same process that triggers solar flares and geomagnetic storms. When solar plasma, carrying tangled magnetic field lines, encounters a comet's ionosphere, field lines can connect, disconnect, and reconnect, releasing energy that accelerates particles and generates observable phenomena. It's elegant physics, magnetic field topology changing in real time, converting stored magnetic energy into the kinetic energy of charged particles. 3I Atlas represents more than just another target for solar weather interactions. As the third confirmed interstellar object, after Oumuamua in 2017 and 2I Borisov in 2019, it carries material formed around a different star in a different stellar system, potentially billions of years ago. If solar storms can alter its behavior, we're witnessing the first documented case of our Sun directly interacting with matter from another stellar neighborhood. The visitor's geometry makes these interactions more likely than they were for previous interstellar objects. Unlike Oumuamua, which passed through the inner solar system quickly and at high inclination to the ecliptic plane, 3I Atlas follows a trajectory that keeps it near the ecliptic, the plane where solar activity tends to concentrate and where Earth experiences most space weather effects. Solar Cycle 25 has provided an active backdrop for these interactions. The 11-year solar cycle reached its current maximum phase during 2024 and 2025, producing elevated sunspot numbers, increased flare frequency, and more frequent coronal mass ejections. The cycle's timing means 3I Atlas is experiencing our star at its most temperamental, subjected to space weather conditions that previous interstellar visitors missed. Observational verification of CME interactions requires careful analysis of brightness changes, spectroscopic variations, and morphological evolution over timescales of hours to days. Professional observatories and amateur astronomers worldwide were monitoring 3I Atlas throughout late September, though initial results remained preliminary as analysis continued. The larger implications extend beyond this single event. If we can document how our Sun influences interstellar material, we gain insights into similar processes throughout the galaxy. Other star systems presumably launch their own coronal mass ejections, potentially altering interstellar objects that pass through their neighborhoods. 3I Atlas might carry signatures of interactions with previous stellar systems encountered during its millions of years' journey through space. As September 2025 drew to a close, the convergence of events, stellar explosions, terrestrial earthquakes, solar storms, and interstellar visitor interactions, created a timeline that challenged comfortable assumptions about cosmic coincidences. Were we witnessing unrelated phenomena clustering by chance, or was something more systematic at work? The answer would emerge as 3I Atlas continued its journey toward a Mars flyby on October 3rd, carrying whatever modifications our Sun's coronal mass ejections might have imposed on this traveler from the stars. Part 5. Weirdness Framed. Step back for a moment and consider what we've mapped. Twin stellar explosions visible to the naked eye. Twin magnitude 6 earthquakes rupturing within hours of each other. Coronal mass ejections threading through the inner solar system. And an interstellar visitor crossing our neighborhood during solar maximum conditions. A lot of universe happening very fast, compressed into the final week of September 2025. This is where honest science meets human pattern recognition, and the collision isn't always comfortable. Our brains evolved to detect meaningful connections in complex environments, the rustle that might signal a predator, the cloud formation that could bring rain, the behavioral changes that might indicate social threat or opportunity. This cognitive architecture serves us well in many contexts, but it can also lead us to perceive significance in coincidental clustering. The scientific mainstream offers clear guidance on these events. The United States Geological Survey maintains no demonstrated connection between space weather phenomena and earthquake occurrence. Decades of correlation studies have failed to establish reliable predictive relationships between solar activity and seismic events. Professional seismologists emphasize that earthquake prediction remains impossible using current scientific methods, whether based on terrestrial precursors or extraterrestrial influences. Similarly, stellar astronomers view novae as predictable consequences of binary star evolution, occurring when white dwarf stars accumulate sufficient material from companion stars to trigger thermonuclear runaway. The timing of nova eruptions follows stellar physics rather than terrestrial or solar system influences. V1935 Centauri and V79994. Sagittarii represent normal, if visually impressive, examples of processes occurring throughout our galaxy on a regular basis. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution in the Sun's corona. These events occur more frequently during solar maximum periods, making late 2025 a statistically likely time for multiple CME events. The interaction between solar storms and cometary material has been documented extensively, representing well-understood plasma physics rather than exotic phenomena. Yet acknowledging mainstream scientific positions doesn't require dismissing the remarkable nature of this temporal cluster. Sometimes the universe arranges itself in ways that stretch coincidence toward something approaching synchronicity. Even if the underlying mechanisms remain mundane, the question becomes, how do we hold space for both rigorous skepticism and appropriate wonder? Our approach throughout this exploration will maintain clear boundaries between different types of claims. Observational facts, magnitude measurements, location coordinates, spectroscopic detections form our foundation. These represent what instruments recorded, what satellites detected, what seismographs measured. Above this foundation, we'll build layers of scientific interpretation based on established physics and well-tested models. Beyond established science lies the realm of speculation, where we'll venture carefully and with clear labeling. Speculative connections, possible relationships between solar activity and terrestrial phenomena, potential influences of stellar events on solar system dynamics, hypothetical mechanisms linking cosmic and geological processes deserve exploration, provided we maintain transparency about their status as hypotheses rather than facts. The vocabulary of cosmic events requires definition for general audiences. A nova represents a stellar explosion that brightens a binary star system by factors of thousands or millions, caused by thermonuclear runaway on a white dwarf surface. It differs fundamentally from a supernova, which destroys the exploding star entirely. A coronal mass ejection consists of billion-ton plasma clouds launched from the Sun at speeds of hundreds to thousands of kilometers per second. Perihelion marks an object's closest approach to the Sun during its orbit. An astronomical unit equals the average Earth-Sun distance, roughly 93 million miles or 150 million kilometers. Ion tails form when solar wind strips electrons from gas molecules in a comet's coma, creating charged particles that follow magnetic field lines straight away from the Sun. These tails can extend millions of kilometers through space, providing visible evidence of invisible magnetic processes operating between stars and smaller bodies. What's coming in our investigation will separate observed phenomena from imagined connections while maintaining respect for both scientific rigor and human curiosity. We'll examine the detailed physics of stellar explosions, earthquake ruptures, and solar storm interactions. We'll track 3I Atlas through its Mars flyby on October 3rd and perihelion approach on October 29th. We'll explore legitimate scientific hypotheses about connections between cosmic and terrestrial phenomena, alongside clearly labeled speculation about more exotic possibilities. The autumn equinox season traditionally amplifies space weather effects through the Russell-McLaren effect, a geometric coupling between Earth's magnetic field and solar wind conditions that often intensifies geomagnetic activity during September and October. This seasonal enhancement provides additional context for why late September might produce elevated space weather activity, independent of any connection to other phenomena. 3I Atlas offers unique scientific opportunities precisely because it represents our third confirmed interstellar visitor and the first observed during highly active solar conditions. The geometry of its trajectory, passing near the ecliptic plane, where most solar system activity concentrates, maximizes the probability of multi-mission observations and space weather interactions. Unlike Oumuamua, which departed quickly before comprehensive study, or 2I Borisov, which remained relatively distant, 3I Atlas provides extended observation opportunities spanning several months. The stakes for October and November extend beyond academic interest. Mars orbiter missions, including ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, have planned opportunistic observations during the October 3rd flyby, potentially providing unprecedented resolution imagery of an interstellar visitor's nucleus and coma structure. Ground-based observatories worldwide continue monitoring brightness changes, spectroscopic evolution, and morphological variations that could reveal how solar weather affects interstellar material. For earthquake monitoring in Venezuela, aftershock sequences typically continue for weeks to months following major ruptures. While seismologists cannot predict whether larger events might occur, they maintain continuous monitoring of regional seismic activity and stress field evolution. The complex tectonics of the Caribbean-South American plate boundary ensures that this region will continue generating earthquakes, though their timing remains fundamentally unpredictable. Our commitment involves presenting multiple perspectives honestly. Mainstream scientific explanations deserve primary attention because they rest on established physics and extensive observational support. Speculative hypotheses deserve consideration, provided they remain clearly distinguished from proven science. The human impulse to find meaning in apparent patterns deserves respect, even when scientific evidence doesn't support causal connections. Perhaps the most remarkable aspect of this convergence involves timing. We live during the first generation in human history capable of detecting interstellar visitors, monitoring global seismic activity in real time, observing stellar explosions across the electromagnetic spectrum, and tracking space weather throughout the solar system. Previous generations might have noticed bright novae and felt earthquake shaking, but they couldn't have connected these phenomena to solar storms and interstellar visitors because the technology to detect such connections didn't exist. We will separate what is observed from what is imagined, what is proven from what is possible, what is likely from what is merely conceivable. So how do stars explode without destroying themselves entirely? The answer reveals physics operating at scales that challenge human intuition. Part 6. Anatomy of a nova picture. A white dwarf star, a sphere roughly the size of Earth, but containing the mass of our entire Sun. Its surface gravity crushes matter to densities approaching 1,000,000 times that of water. Surface temperatures hover around 50,000 degrees Celsius. This stellar corpse represents what remains after a sun-like star exhausts its nuclear fuel, sheds its outer layers, and collapses into a sphere of degenerate matter, where atoms exist in states impossible under terrestrial conditions. Now imagine this cosmic furnace locked in an orbital dance with a normal star, perhaps a red giant whose outer atmosphere has swollen to massive proportions as it ages. Gravity from the white dwarf gradually strips hydrogen from its companion's extended atmosphere, pulling gas across the space between stars in streams that spiral inward like water circling a drain. This stolen material accumulates on the white dwarf's surface, growing denser and hotter under the crushing gravitational compression. For decades, centuries, or millennia, hydrogen accumulates. Temperature and pressure climb steadily as more material piles onto the white dwarf's surface. Unlike the controlled nuclear fusion occurring in stellar cores, this process builds toward explosive release. When temperature reaches roughly 100 million Kelvin, thermonuclear runaway begins. The explosion that created V1935 Centauri occurs in seconds. Runaway fusion consumes the accumulated hydrogen layer in a conflagration that releases energy equivalent to our sun's total output over thousands of years. But here's the crucial difference from a supernova. The white dwarf itself survives. The explosion blows away only the surface layer of stolen material, leaving the underlying stellar remnant intact and ready to begin the process again. This is why V1935 Centauri's high-energy signatures captured the attention of space-based observatories worldwide. When NASA's Fermi Gamma Ray Space Telescope detected gamma rays from the nova's direction, it was recording evidence of particles accelerated to near-light speeds in the explosion's shock fronts. The Swift Observatory's hard X-ray detections revealed electrons spiraling through magnetic fields at enormous energies, creating synchrotron radiation across the electromagnetic spectrum. These high-energy phenomena transform novae from simple brightening events into cosmic particle accelerators. The expanding shell of ejected material, racing outward at speeds of several thousand km/s, creates shock waves when it collides with the sparse gas between stars. These shocks function like natural cyclotrons, using magnetic fields to accelerate protons and electrons to energies that would require massive terrestrial laboratories to achieve. The American Association of Variable Star Observers coordinates amateur contributions to nova science through standardized photometry protocols. Visual observers. Estimating brightness and the role of amateur astronomers. Astronomers estimate a nova's brightness by comparing it to nearby stars of known magnitude, while visual observers use binoculars or small telescopes for such comparisons. CCD cameras provide precise photometric measurements that reveal subtle variations in the nova's light curve. These observations, contributed by hundreds of amateur astronomers worldwide, deliver the high temporal resolution that professional observatories, focused on numerous targets, cannot maintain for individual objects. V1935. Centauri's brightness evolution follows patterns established by decades of nova studies. The initial rise from invisibility to naked-eye magnitude typically occurs over days to weeks. Peak brightness may last anywhere from days to months, depending on the white dwarf's mass, the accretion rate from its companion star, and the composition of the ejected material. The decline phase can extend over months or even years, sometimes interrupted by secondary peaks as different physical processes dominate the nova's energy output. Spectroscopic insights. Spectroscopy reveals the nova's chemical fingerprints. Early spectra typically show broad emission lines of hydrogen, helium, and heavier elements moving at high velocities, evidence of the rapidly expanding ejecta. As the nova evolves, these lines narrow and shift as the ejected material cools and decelerates. Eventually, forbidden lines appear. transitions that can only occur in the extremely low-density environments of expanding nova shells, where atoms may go hours or even days between collisions. Cosmic distances and historical context. The distances to V1935 Centauri and V7994 Sagittaria remain uncertain but likely exceed several thousand light-years. This means the explosions we observed in September 2025 actually occurred millennia ago, around the time human civilization was just beginning to develop agriculture and permanent settlements. The light from these stellar explosions has been traveling through interstellar space longer than recorded human history, arriving at Earth precisely during this remarkable week. Amateur contributions to nova science. Amateur astronomers can contribute meaningful observations using modest equipment. Digital single-lens reflex, DSLR, camera with a telephoto lens can record both novae during their bright phases. Visual observers using binoculars or small telescopes can estimate magnitudes by comparing the nova to nearby stars of known brightness. More sophisticated observers equipped with CCD cameras and photometric filters provide precision data that supplements professional observations. Naming conventions. The naming system for nova designations reflects astronomical tradition and administrative processing. V1935 Centauri received its permanent variable star designation as the 1235th officially catalogued variable star in the constellation Centaurus. The V prefix indicates a variable star, an object whose brightness changes over time. This permanent designation replaces temporary discovery names that might include the discoverer's surname, the date of discovery, or catalog numbers from various survey programs. Dust formation in novae. Dust formation represents one of the most intriguing aspects of nova evolution. Weeks to months after the initial explosion, some novae experience dramatic dimming as newly formed dust grains condense in the cooling ejecta. These dust dip events can reduce a nova's brightness by several magnitudes as microscopic particles absorb and scatter its light. Eventually, the dust either disperses or is destroyed by the nova's continuing radiation, allowing the underlying stellar remnant to become visible again. Energy scales. Novae versus supernovae. The energy scales involved in nova explosions dwarf human experience, yet remain modest compared to supernovae. A typical nova releases energy equivalent to the Sun's total output over roughly 10,000 years, enough to power human civilization for billions of years at current consumption rates. Yet this represents only a tiny fraction of the energy released in supernova explosions, which can outshine entire galaxies for weeks or months. Recurrent novae and stellar evolution. Recurrent novae complicate the simple picture of single explosive events. Some white dwarf systems undergo nova eruptions on relatively predictable timescales, every few decades in the case of the most frequent repeaters. These systems may experience dozens of nova explosions over astronomical time, gradually accreting enough material to approach the Chandrasekhar mass limit, at which point the white dwarf itself could explode as a Type Ia supernova. Multi-wavelength follow-up. Professional follow-up observations of both September novae continue across multiple wavelengths of the electromagnetic spectrum. Ground-based telescopes monitor optical brightness changes and spectroscopic evolution. Space-based observatories, including the Hubble Space Telescope, may obtain high-resolution images of the expanding nova shells. Radio telescopes can detect synchrotron emission from relativistic particles in the nova ejecta. Classification and exotic possibilities. The classification of V1935 Centauri and V7994 Sagittarii as classical novae, rather than other types of stellar explosions, is based on spectroscopic evidence and brightness evolution patterns. Dwarf novae, caused by instabilities in accretion disks rather than thermonuclear explosions, typically show different spectral characteristics and smaller amplitude brightenings. Luminous red novae, possibly caused by stellar mergers, display different colors and evolution timescales. Could either of these novae represent something more exotic than standard thermonuclear explosions? Current observational evidence supports classical nova interpretations, but astronomy maintains healthy skepticism about initial classifications. As more data accumulates from multi-wavelength observations, the detailed physics may reveal subtleties that refine our understanding of these particular explosions. Gamma-ray novae, the gamma-ray detection from V1935 Centauri, places it among an emerging class of gamma-ray novae that challenge traditional models of nova physics. These high-energy emissions suggest particle acceleration processes operating more efficiently than previously thought possible in nova environments. The underlying physics may involve magnetic reconnection, shock acceleration, or other mechanisms that bridge the gap between nova explosions and more energetic phenomena like supernova remnants. Part 7. Anatomy of a quake cluster. As we tracked these stellar explosions across the electromagnetic spectrum, Earth's solid surface was preparing to demonstrate that our planet's interior could be every bit as dynamic as distant stars. Beneath Lake Maracaibo and the surrounding Zulia state of Venezuela lies one of South America's most tectonically complex regions. The Caribbean plate grinds against the South American plate along a boundary zone that includes multiple fault systems. The Boconó Fault System, running northeast-southwest through the Venezuelan Andes. The Oca Ancon Fault, trending east-west along the Caribbean coast. And the Santa Marta Fault, extending into Colombia. These geological boundaries have been accumulating stress for decades, storing energy that must eventually be released through sudden slip events. The magnitude 6.2 earthquake at 22:21 UTC on September 24th began as a rupture along one of these fault segments, approximately 7.0 kilometers beneath the surface. At this relatively shallow depth, seismic waves had less opportunity to spread out and weaken during their journey to the surface, amplifying ground acceleration across a broad region. The initial rupture likely extended several kilometers along the fault plane, with sudden displacement measured in meters, releasing stress that had been building for years or decades. Seismic waves propagated outward from the rupture zone at roughly 6 kilometers through the surrounding rock. Primary P waves, compressional disturbances that cause back-and-forth motion along their direction of travel, arrived first at seismograph stations across the region. Secondary S waves followed, creating the side-to-side motion that typically causes the most damage to structures. Surface waves, traveling more slowly but often carrying the most destructive energy, produced the rolling motions that eyewitnesses described as lasting for minutes in some locations. Just 5.5 hours later, at 03:51 UTC on September 25th, a second major rupture struck virtually the same region. The magnitude 6.3 earthquake originated from a depth of 14 km, deeper than its predecessor, but still shallow enough to generate intense surface shaking. This second event likely occurred on an adjacent fault segment, triggered by stress changes created by the first rupture. The physics of stress transfer explains why earthquakes often occur in clusters. When one fault segment suddenly slips, it alters the stress field on nearby segments. Some areas experience increased stress, making them more likely to rupture soon after. Others experience stress relief, becoming temporarily less prone to failure. The September 24th rupture apparently loaded stress onto the fault segment that failed 5.5 hours later. The magnitude difference between the 6.2 and 6.3 earthquakes might seem trivial, but due to the logarithmic nature of the magnitude scale, the second event released approximately twice as much energy as the first. Combined, these twin ruptures produced energy equivalent to a single magnitude 6.4-6.5 earthquake, a significant release that ranks among the largest global seismic events of late September 2025. International seismological agencies reported slightly different magnitudes for these events, reflecting the complexities of earthquake measurement. The United States Geological Survey, USGS, uses moment magnitude, calculated from the total energy released during rupture. The European Mediterranean Seismological Center, EMSC, may use different magnitude scales based on surface wave amplitudes or body wave characteristics. These methodological differences, combined with updates as additional seismograph data become available, explain why headlines reported magnitude ranges from 6.1 to 6.3 for the first event. The aftershock sequence followed patterns seismologists have documented for decades. The magnitude 5.8 earthquake that struck later on September 25th represents a typical large aftershock, smaller than the main shock, but still significant enough to cause additional damage and concern. Omori's law, formulated in the early 1900s, describes how aftershock frequency decays over time following major earthquakes. The largest aftershocks typically occur within days of the main shock, with smaller events continuing for weeks, months, or even years. Human impact and regional geology. Human impact from these earthquakes extended across both Venezuela and Colombia. The relatively shallow depths amplified surface shaking, leading to evacuation orders for high-rise buildings in major cities. Social media filled with videos of swinging light fixtures, rattling windows, and people evacuating buildings as emergency protocols activated across the region. While initial damage reports remained limited given the earthquake's magnitudes, assessment teams spent days documenting both visible structural damage and potential long-term weakening of buildings and infrastructure. The regional geology helps explain why this area generates such powerful earthquakes. The Maracaibo Basin formed through complex interactions between the Caribbean and South American plates, creating a network of fault systems that accommodate ongoing tectonic motion. Lake Maracaibo itself sits within a graben, a down-dropped block bounded by normal faults that continue to experience active deformation. The petroleum deposits that make this region economically important, formed in sedimentary basins created by the same tectonic processes that generate earthquakes. Depth uncertainty and triggering mechanisms. Depth measurements carry significant uncertainty, especially in geologically complex regions. The 7.8 kilometers depth reported for the first event and 14 kilometers for the second represent best estimates based on seismic wave arrival times at multiple monitoring stations. These depths place both earthquakes in the upper crust, where brittle fracture dominates over the ductile deformation that occurs at greater depths under higher temperature and pressure. The timing of these events raised questions about potential triggers. Could solar activity, atmospheric pressure changes, or other external factors influence earthquake occurrence? The scientific consensus, supported by the USGS and international seismological organizations, maintains that no reliable correlation exists between space weather and earthquake activity. Decades of statistical analysis have failed to establish predictive relationships between solar flares, coronal mass ejections, geomagnetic storms, and seismic events. However, some research has explored more subtle potential connections. Changes in atmospheric pressure can alter stress on fault systems by tiny amounts, typically far smaller than the stress changes caused by earth tides from lunar and solar gravitational effects. While these influences remain detectable with sensitive instruments, they fall orders of magnitude below the stress changes needed to trigger earthquakes on faults that aren't already very close to failure. Fault mechanics and forecasting. The Global Centroid Moment Tensor (GCMT) database provides detailed analyses of fault orientations, slip directions, and rupture mechanisms for both Venezuelan earthquakes. Beach ball diagrams derived from this data reveal which fault planes actually moved and in what directions. Information that helps seismologists understand regional stress fields and predict which fault segments might experience elevated risk in the future. Statistical seismology offers the only reliable approach to earthquake forecasting currently available. Following major earthquakes like those in Venezuela, the probability of additional large events in the same region increases temporarily due to aftershock activity and stress transfer effects. However, this increased probability typically lasts weeks to months and cannot specify exactly when or where additional earthquakes might occur. Building codes and emergency preparedness systems face continuous testing in seismically active regions like Zulia State. The relatively moderate damage reports following magnitude 6.2 and 6.3 earthquakes likely reflect both fortunate timing and ongoing improvements in construction standards. Modern seismic building codes require structures to withstand strong ground shaking, though older buildings may remain vulnerable to damage or collapse. Could larger earthquakes follow in the same region? The geological setting certainly allows for more powerful events. The fault systems around Lake Maracaibo have generated magnitude 7 earthquakes historically, and regional tectonics suggest such events will continue occurring irregularly over geological time. However, seismologists cannot predict whether days, years, or decades might pass before the next major rupture. The Venezuelan earthquake sequence demonstrates how solid Earth processes can produce dramatic energy releases over human timescales while following physical laws that operate over geological time. Stress accumulates slowly as tectonic plates grind past each other at rates of centimeters per year. When accumulated stress exceeds rock strength, sudden failure releases decades or centuries of stored energy in seconds to minutes of violent shaking. Part 8. The Sun at Maximum. As aftershocks continued to rattle the Caribbean-South American plate boundary, our attention turned to the space environment, where another type of energy release was unfolding at scales that dwarf terrestrial earthquakes. Solar Cycle 25 reached its peak activity during 2024 and 2025, transforming our typically well-behaved star into a restless giant capable of hurling billion-ton plasma clouds across the solar system. On September 24th and 25, stellar explosions lit up southern skies, while earthquakes shook Venezuelan bedrock. Solar activity indices painted a picture of a sun operating near maximum fury. The 10.7 centimeter radio flux, a key indicator of solar activity, hovered around 180 to 190 solar flux units during late September. This measurement, taken daily by radio telescopes, correlates strongly with the number and intensity of active regions on the Sun's surface. Values above 150 typically indicate elevated solar activity. Readings above 200 suggest very active conditions capable of producing major space weather events. Sunspots themselves tell the story of magnetic chaos unfolding in the Sun's photosphere. These dark regions, often larger than Earth, form where powerful magnetic field lines punch through the solar surface and suppress normal convective heat transport. Magnetic field strength in sunspot cores can exceed 3,000 Gauss, roughly 6,000 times stronger than Earth's surface magnetic field. More sunspots generally mean more opportunities for magnetic field lines to tangle, reconnect, and explosively release energy as solar flares and coronal mass ejections, CMEs. but raw sunspot numbers only hint at the complexity of solar maximum conditions. The sun's magnetic field during peak activity resembles a twisted, knotted mess rather than the relatively simple dipole field that dominates during solar minimum. Active regions, collections of sunspots connected by loops of magnetic field, can persist for weeks or months, rotating across the solar disk and occasionally producing spectacular eruptions visible to spacecraft throughout the inner solar system. Coronal mass ejections and space weather. Coronal mass ejections represent the most dramatic manifestation of solar maximum physics. These events begin when magnetic field lines in the sun's corona become so twisted and stressed that they suddenly snap and reconnect, converting magnetic energy into kinetic energy of charged particles. The process launches billion-ton clouds of plasma into space at speeds ranging from 250 km/s for slow events to over 3,000 km/s for the fastest eruptions. NOAA's Space Weather Prediction Center tracks these solar storms using the WSA Enlil model, a sophisticated computer simulation that maps CME propagation through the heliosphere. The model divides space into a three-dimensional grid extending from the Sun to beyond Earth's orbit, calculating how solar wind speed, density, and magnetic field orientation evolve as plasma clouds travel through the solar system. While Enlil excels at predicting general arrival times and intensities, it cannot capture every detail of CME structure and behavior. The autumn equinox season traditionally amplifies space weather effects through a phenomenon known as the Russell-McFerrin effect. This geometric coupling arises from the orientation of Earth's magnetic field relative to the interplanetary magnetic field carried by the solar wind. During equinox periods, the geometry favors magnetic reconnection between the solar wind's magnetic field and Earth's magnetosphere, often producing intense geomagnetic storms, even from relatively modest solar disturbances. Impacts of space weather impacts extend far beyond the aurora displays that capture public attention. Geomagnetic storms can disrupt high-frequency radio communications used by aviation and maritime industries, force satellite operators to adjust spacecraft orbits due to increased atmospheric drag, and, in extreme cases, threaten power grid stability through geomagnetically induced currents. NOAA maintains standardized scales for space weather effects: the G scale for geomagnetic storms, the S scale for solar radiation storms, and the R scale for radio blackouts. These help various industries prepare for and respond to space weather events. Comets as plasma laboratories. The interaction between coronal mass ejections and comets provides a natural laboratory for studying plasma physics under conditions impossible to recreate on Earth. Ion tails form when the solar wind strips electrons from gas molecules in a comet's coma, creating charged particles that follow magnetic field lines directly away from the Sun. These tails can extend millions of kilometers through space, providing visible evidence of invisible magnetic processes operating between our star and smaller bodies in the solar system. When a CME encounters a comet, the interaction can be dramatic and visually spectacular. The European Space Agency's stereo satellites documented such an event in 2007 when a coronal mass ejection completely severed Comet Encke's ion tail through magnetic reconnection processes. The disconnected tail drifted away from the comet over several hours, while a new tail formed from fresh material, demonstrating the dynamic nature of space weather interactions. Interstellar visitors in an active solar environment, solar maximum conditions during 2025, provided an active backdrop for 3I Atlas as it approached the inner solar system. Unlike previous interstellar visitors that encountered our Sun during quieter phases of the solar cycle, This object experienced space weather effects near peak intensity. The combination of elevated CME frequency and the visitor's trajectory through the ecliptic plane, where most solar system activity is concentrated, maximized the probability of significant interactions. Physics of CME propagation. The physics of CME propagation involves complex magnetohydrodynamics operating over scales ranging from individual particle motions to structures larger than planetary orbits. Fast CMEs can overtake slower solar wind, creating compression regions and shock fronts that accelerate particles to high energies. Multiple CMEs can interact with each other, merging into larger, more powerful disturbances or creating complex magnetic field configurations that enhance particle acceleration and magnetic reconnection. Monitoring the Sun. Professional space weather forecasters monitor multiple data sources to track solar activity and predict Earth impacts. The Solar Dynamics Observatory, SDO, provides continuous, high-resolution images of the Sun's surface and corona in multiple wavelengths of extreme ultraviolet light. The Solar and Heliospheric Observatory, SOHO, watches for CMEs erupting from the Sun's far side. The Advanced Composition Explorer, AC, positioned between Earth and the Sun, provides advanced warning of incoming solar wind disturbances. Amateur radio operators serve as an informal global network for monitoring space weather effects on Earth. High-frequency radio propagation changes dramatically during geomagnetic storms, sometimes improving long-distance communications through enhanced ionospheric reflection, while degrading others through increased absorption and scattering. These real-time reports complement formal measurements from professional monitoring stations. The shape of solar maximum. The current solar maximum appears to be following a double-peaked pattern seen in some previous cycles, with an initial peak in activity during 2024 followed by cosmic convergence. The universe's most synchronized spectacle continued high activity through 2025. This extended maximum phase means elevated space weather risks may persist longer than typical 11-year cycles, maintaining conditions favorable for dramatic solar-terrestrial interactions well into 2026. Aurora photography and observation have become increasingly popular during the current solar maximum, with social media filled with spectacular images of green, red, and purple lights dancing across polar and subpolar skies. These displays result from charged particles from solar storms interacting with Earth's upper atmosphere, exciting oxygen and nitrogen atoms that emit characteristic colors when they return to ground states. The solar wind itself carries embedded magnetic fields that originated in the Sun's corona and stretched across the solar system as plasma flows outward. These interplanetary magnetic field lines connect planets, comets, and spacecraft in a vast web of electromagnetic influence, extending to the heliopause, the boundary where solar wind pressure balances interstellar medium pressure, roughly 100 times farther from the Sun than Earth. As we tracked solar storms propagating through the inner heliosphere during late September 2025, one particular target captured the attention of space weather forecasters and astronomy enthusiasts alike. An interstellar visitor threading through this cosmic storm system on approach to its first encounter with another world. Part 9. 3I Atlas on approach. In the early morning hours of July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS telescope array, detected something extraordinary moving against the background stars. Initial observations suggested a faint, comet-like object, but orbital calculations quickly revealed its true nature. 3I Atlas, only the third confirmed interstellar visitor in human history. Following the mysterious Oumuamua in 2017 and comet 2I Borisov in 2019. The designation tells the story of its discovery and significance. The 3I prefix indicates the third interstellar object catalogued by the International Astronomical Union, while Atlas credits the telescope system that first spotted this cosmic wanderer. Unlike its predecessors, 3I Atlas arrived during a uniquely favorable observation window, bright enough for detailed study, following a trajectory that keeps it near the ecliptic plane, where most solar system activity concentrates, and approaching during solar maximum conditions that offer unprecedented opportunities to study how our star influences interstellar material. The visitor's orbital characteristics reveal its alien origins. Its trajectory shows a hyperbolic shape with an eccentricity significantly greater than 1, indicating it possesses more than enough speed to escape the Sun's gravitational influence. The orbital inclination of approximately 175 degrees means 3I Atlas moves in a retrograde direction relative to the planets, backward compared to the normal flow of solar system traffic. Current models suggest the object measures somewhere between several hundred meters and possibly up to 15 kilometers across. Though these size estimates carry substantial uncertainty, direct imaging remains impossible even for the largest ground-based telescopes. The visitor appears as nothing more than a fuzzy, star-like point of light, surrounded by a faint coma of gas and dust. Size estimates depend on assumptions about the object's reflectivity, composition, and activity level, all unknown quantities for an object formed around a different star. October 3, 2025 marks a pivotal moment in interstellar visitor science. 3I Atlas will pass within 0.19 astronomical units of Mars, roughly 28 to 30 million kilometers from the red planet. This close approach offers unprecedented opportunities for detailed observations using Mars orbital missions, including ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and other spacecraft positioned to study the visitor from a cosmic front-row seat. Harvard astronomer Avi Loeb described the Mars encounter as a blind date between an interstellar visitor and our neighboring world. The Mars Reconnaissance Orbiter's high-rise camera, capable of resolving features as small as 30 centimeters on the Martian surface, should achieve pixel scales of roughly 30 kilometers when pointed toward 3I Atlas during closest approach. While this resolution won't reveal surface details of the visitor's nucleus, it may distinguish between a compact central condensation and a more diffuse coma structure. The scientific value of these observations extends beyond simple imaging. Spectrographic measurements during the Mars flyby could reveal the chemical composition of gas escaping from the visitor's nucleus as solar heating liberates ancient volatile compounds. Expected spectral lines include CN, cyanogen, CO, carbon monoxide, and CO2, carbon dioxide, molecules that would provide direct evidence of the visitor's chemical makeup and clues about conditions in its birth stellar system. Amateur astronomers worldwide have contributed crucial observations of 3I Atlas throughout its approach. Early reports suggested faster-than-expected brightening as the object moved closer to the Sun. Though these preliminary light curves require careful calibration and confirmation, the visitor's southern sky position favors observers in the southern hemisphere, though northern observers can track it during early morning hours when it rises above their southern horizon. Professional observatories continue coordinating observation campaigns through organizations like the American Association of Variable Star Observers, AAVSO, and the Minor Planet Center. These efforts aim to characterize brightness variations, tail morphology changes, and spectroscopic evolution. As 3I Atlas responds to increasing solar heating during its inbound journey, The visitor's trajectory through the inner solar system offers multiple observation opportunities extending through early 2026. Following the Mars flyby on October 3rd, 3I Atlas continues toward perihelion, its closest solar approach, on October 29th at approximately 136 to 1.4 astronomical units from the Sun. This distance keeps it outside Earth's orbit, but well within the range of ground-based telescopes and space-based observatories. December 19th marks 3I Atlas's closest approach to Earth at roughly 1.8 astronomical units, about 270 million kilometers. For comparison, this is closer than Mars at its most distant point from Earth, providing excellent viewing conditions for both professional observatories and amateur astronomers with modest telescopes throughout late 2025 and early 2026. The visitor's behavior near perihelion could reveal whether it follows typical comet evolution patterns or displays unique characteristics reflecting its interstellar origins. Solar heating may liberate volatile compounds that have remained frozen for millions of years during the object's journey through interstellar space. The resulting outgassing could produce dramatic brightness increases, tail development, or other phenomena that distinguish interstellar visitors from solar system comets. Tail morphology represents one of the most intriguing aspects of 3I Atlas observations. Professional images show anti-sunward ion features consistent with typical comet behavior, while some amateur observers report forward-looking dust structures that appear to violate normal comet physics. These apparent contradictions likely reflect the different physics governing dust and ion tail formation, rather than exotic phenomena. Dust tails form through radiation pressure, the gentle but persistent force of sunlight striking microscopic particles liberated from the comet's nucleus. These particles follow curved trajectories as they respond to both solar radiation pressure and gravitational attraction, creating the graceful, curved tails visible in most comet photographs. Dust tails can appear to point in various directions, depending on viewing geometry and the observer's position relative to the comet's orbital plane. Ion tails form through entirely different physics. Solar wind strips electrons from gas molecules in the comet's coma, creating charged particles that become electromagnetically coupled to magnetic field lines embedded in the solar wind. These charged particles flow straight away from the Sun along magnetic field lines, creating the narrow, straight tails that change direction as solar wind magnetic field orientation varies. The size and composition uncertainties surrounding 3I Atlas reflect the fundamental challenges of studying objects at interplanetary distances. Even the most powerful telescopes cannot resolve surface details of objects smaller than major asteroids at ranges exceeding several astronomical units. Size estimates depend on brightness measurements, assumptions about surface reflectivity, and models of how much light the object scatters toward Earth. Some media reports have speculated that 3I Atlas could measure up to 15 kilometers across, but these estimates should be treated cautiously until resolved through thermophysical modeling that combines brightness measurements with infrared observations of thermal emission. The object's activity level, how much gas and dust it produces relative to its size, also influences apparent brightness in ways that complicate size determinations. The visitor's approach coincides with another spectacular celestial event that promises to make October 2025 a memorable month for skywatchers worldwide. But first, we need to understand what happens when our Sun's coronal mass ejections collide with objects that have spent eons wandering between the stars. Part 8. Comet C2025 R2 Swan, the Solar System's surprise guest. While 3I Atlas captures headlines as an interstellar visitor, October 2025 promises a second celestial spectacular that could steal the show. Comet C2025 R2 discovered in SOHO SWAN data by amateur astronomer Vladimir Bezugli on September 11th and 12th, is racing toward its closest approach to Earth on October 20th and 21st, potentially reaching naked-eye brightness during the same weeks that 3I Atlas performs its Mars flyby. The discovery story itself demonstrates the power of citizen science in modern astronomy. SOHO, the Solar and Heliospheric Observatory, continuously monitors the Sun's corona and surrounding space environment. Its SWAN, solar wind anisotropies, instrument maps hydrogen emissions throughout the heliosphere, occasionally detecting comets as they brighten and begin outgassing while approaching the inner solar system. Vladimir Bezugli, scanning through publicly available SWAN data, noticed a brightening object that didn't match any known comet or asteroid. His careful analysis of multiple images confirmed the object's cometary nature and provided preliminary orbital calculations, suggesting a long-period comet making its first recorded approach to the inner solar system in human history. Comet SWAN reached perihelion, its closest approach to the Sun, on September 12, 2025, just days after its discovery. This timing explains the rapid brightening that initially caught Bezugli's attention. Comets typically brighten most dramatically as they approach perihelion, when increasing solar heating liberates volatile compounds from their nuclei and creates the characteristic coma and tail structures that make them visible from Earth. The orbital geometry favors October observations from both hemispheres, though southern observers initially enjoyed superior viewing conditions. As October progresses, the comet's position relative to Earth and the Sun improves for northern hemisphere observers, potentially offering excellent viewing opportunities for the largest number of amateur astronomers and casual skywatchers. Current brightness predictions suggest Comet SWAN could reach magnitude 4 to 6 during its closest approach to Earth, bright enough for naked-eye visibility under dark skies, though binoculars or small telescopes would reveal far more detail of its coma and tail structure. These brightness estimates carry substantial uncertainty because comet behavior remains notoriously unpredictable, especially for new comets making their first recorded approach to the inner solar system. The timing creates a perfect confluence of celestial events during late October 2025. The new moon phase around October 20th and 21st eliminates lunar interference that often washes out faint celestial objects. The annual Orionid meteor shower reaches peak activity during the same nights, created by debris from Comet Halley intersecting Earth's orbit. Skywatchers could potentially observe a bright comet, multiple meteors per hour, and the continuing evolution of 3I Atlas, all during the same optimal viewing sessions. Comet SWAN's status as a long-period solar system comet contrasts sharply with 3I Atlas's interstellar origins. While both objects likely contain similar volatile compounds, water ice, carbon monoxide, carbon dioxide, and various organic molecules, they formed in entirely different environments. Comet SWAN condensed from material in the outer regions of our own solar system roughly 4 billion years ago, possibly spending most of its existence in the distant Oort cloud before gravitational perturbations sent it sunward. The scientific questions posed by each object differ accordingly. 3I Atlas offers insights into stellar system formation processes, interstellar chemistry, and how cosmic radiation affects materials during million-year journeys between stars. Comet SWAN provides information about conditions in the early solar system, the composition and structure of the Oort cloud, and how solar heating affects pristine cometary materials, making their first close approach to the Sun. Photographic opportunities abound for both professional and amateur astronomers during October's double comet spectacle. Wide-field cameras can capture both objects in the same frame, documenting their relative positions, brightness, and tail structures for comparison. Time-lapse photography could reveal changes in coma morphology, tail orientation, and overall brightness as solar wind conditions vary, and the object's distances from Earth and the Sun change daily. The unpredictable nature of comet brightness evolution adds excitement and uncertainty to October's viewing prospects. Some comets exceed brightness predictions dramatically, developing spectacular tails and reaching magnitudes that make them unmistakable naked-eye objects, even from light-polluted urban areas. Others disappoint, failing to brighten as expected or fragmenting under solar heating stress in ways that diminish their visual impact. Comet Swan's short observational history makes reliable predictions particularly challenging. Unlike periodic comets that return regularly and allow astronomers to study their behavior patterns over multiple apparitions, new long-period comets like Swan offer no historical precedent for their outgassing rates or structural stability under solar heating. The potential for dramatic tail development adds visual appeal to October's comet viewing opportunities. Both dust and ion tails could become prominent features as solar wind activity continues at elevated levels during solar maximum conditions. Disconnection events, where coronal mass ejections sever ion tails from comet nuclei, might become visible in real time through telescopic observations, offering rare glimpses of space weather physics in action. Amateur comet observers employ various techniques to track brightness changes and morphological evolution. Visual magnitude estimates compare comet brightness to nearby stars of known magnitude, providing data that professional observatories cannot obtain continuously. Photographic methods using digital cameras and CCD systems provide more precise measurements while documenting structural changes in coma and tail features. The question of whether Earth might encounter debris from Comet Swan adds speculative interest to October's observations. If our planet's orbit intersects the comet's dust trail from previous passages through the inner solar system, we might experience a minor meteor shower as particles enter Earth's atmosphere. However, such events remain highly uncertain for newly discovered comets without well-established debris trails. Spectroscopic observations of both comets during October could reveal chemical similarities and differences that illuminate their formation histories. Professional observatories equipped with spectrographs can detect emission lines from specific molecules, CN, C2, O, NH2, that indicate which volatile compounds are sublimating from each nucleus under solar heating. These chemical fingerprints provide direct evidence of composition and formation conditions. The viewing logistics for October's double comet display favor observers with dark skies and clear horizons. Urban light pollution significantly reduces the visibility of faint celestial objects, making rural or wilderness viewing sites essential for optimal comet observation. Weather patterns during late October vary significantly by geographic location, requiring flexible planning for successful observations. Binoculars often provide better comet viewing than telescopes for casual observers. The wide field of view shows the complete comet, nucleus, coma, and tail, in context, rather than magnifying small portions that may lose the overall visual impact. 750 or 10x50 binoculars represent optimal choices, providing enough light-gathering power to reveal faint details while maintaining comfortable viewing angles. The convergence of two bright comets during October 2025 offers unprecedented opportunities for comparative observations. Side-by-side viewing could reveal differences in coma color, tail orientation, and overall morphology that reflect their different origins and evolutionary histories. Time-lapse photography spanning several nights could document how each object responds to changing solar wind conditions and viewing geometry. Professional observatories worldwide have coordinated observation campaigns for both objects, ensuring comprehensive coverage across multiple wavelengths of electromagnetic radiation. The Hubble Space Telescope may obtain high-resolution images that resolve structural details impossible to detect from ground-based observatories. Radio telescopes could detect molecular emission lines that reveal chemical composition and temperature structure within the expanding coma regions. The safety considerations for comet observation remain minimal compared to solar or lunar eclipse viewing. Comets pose no direct threat to observers and require no special filters or protective equipment beyond normal precautions for nighttime outdoor activities. The primary challenges involve finding dark viewing sites, dealing with weather conditions, and maintaining equipment functionality during potentially cold October nights. Educational opportunities multiply when two spectacular comets grace the same sky during optimal viewing conditions. Schools, astronomy clubs, and public observatories often organize special viewing events that introduce newcomers to comet science while providing experienced observers with opportunities to compare objects of fundamentally different origins. These events foster scientific literacy while celebrating the wonder of cosmic phenomena visible to anyone willing to step outside and look up. As October 2025 approaches, the stage is set for a month of unprecedented celestial activity, an interstellar visitor threading past Mars, a long-period comet reaching peak brightness, active solar weather conditions, and continuing aftershock sequences from Venezuelan earthquakes. The convergence of phenomena spanning scales from terrestrial seismology to interstellar astronomy creates a timeline that challenges comfortable assumptions about cosmic coincidences. But before we explore the deeper questions raised by this remarkable clustering of events, we need to examine the patterns that human minds inevitably perceive when dramatic phenomena converge in time and space. Part 11. Cosmic coincidences or patterns. Let's construct a timeline that captures the remarkable clustering of events during late September and early October 2025. September 23rd, V9-35. Centauri erupts to naked eye visibility in Centaurus. September 24th, magnitude 6.2 earthquake strikes Venezuela at 22:21 UTC. September 25th, Vi-7994, Sagittarius explodes in Sagittarius. Magnitude 6.3 earthquake ruptures the same Venezuelan region at 2 hours after the first. Magnitude 5.8 aftershock follows. Late September. Enlil models predict coronal mass ejections crossing 3I Atlas's trajectory. October 3rd. Interstellar visitor flyby of Mars at 0.19 astronomical units. October 20th to 21st. Comet Swan closest approach to Earth, coinciding with new moon and Orionid meteor shower peak. October 29th. 3I. Atlas reaches perihelion at 136 astronomical units from the Sun. This temporal compression of dramatic events across multiple domains, stellar explosions, terrestrial earthquakes, solar weather, and interstellar visitor dynamics, creates a narrative structure that feels almost scripted. Two stars explode within days. Two major earthquakes rupture within hours. Solar storms thread through space during the same week. An interstellar visitor approaches Mars, while a solar system comet reaches peak brightness. The clustering transcends simple coincidence and approaches something resembling cosmic synchronicity. Human brains evolved to detect meaningful patterns in complex environments, a cognitive capability that served our ancestors well when survival depended on recognizing subtle correlations between environmental conditions and potential threats or opportunities. This pattern recognition architecture operates automatically, often below conscious awareness, scanning for connections that might indicate causation, even when only correlation exists. Apophenia, the tendency to perceive meaningful patterns in random information, represents both a strength and a potential weakness of human cognition. The same mental processes that allowed our ancestors to recognize seasonal changes, predict weather patterns, and identify social dynamics can also lead us to perceive significance in coincidental clustering of unrelated events. The scientific mainstream offers clear guidance on the September-October convergence. The United States Geological Survey maintains that no demonstrated physical mechanism connects space weather phenomena to earthquake occurrence. Decades of correlation studies have failed to establish reliable predictive relationships between solar activity and seismic events. Professional seismologists emphasize that earthquake prediction remains impossible using current methods, whether based on terrestrial precursors or extraterrestrial influences. Similarly, cosmic convergence, the universe's most synchronized spectacle, continued. Similarly, stellar astronomers view novae as predictable consequences of binary star evolution, occurring when white dwarf stars accumulate sufficient material from companion stars to trigger thermonuclear runaway. The timing of nova eruptions follows stellar physics rather than terrestrial or solar system influences. V1935 Centauri and V7994 Sagittarii represent normal, if visually impressive, examples of processes occurring throughout our galaxy on a regular basis. Solar physicists study coronal mass ejections as natural consequences of magnetic field evolution in the sun's corona during solar maximum conditions. These events occur more frequently during peak solar activity periods, making late 2025 a statistically likely time for multiple CME events. The interaction between solar storms and cometary material represents well-understood plasma physics rather than exotic phenomena. Yet acknowledging mainstream scientific positions doesn't require dismissing the remarkable nature of this temporal cluster. Sometimes the universe arranges itself in ways that stretch coincidence toward something approaching poetry, even when underlying mechanisms remain mundane. The question becomes, how do we hold space for both rigorous skepticism and appropriate wonder? The both-and approach allows us to appreciate the statistical clustering while respecting scientific boundaries. We can acknowledge that twin novae reaching naked-eye brightness within days represents an uncommon occurrence, without invoking causal connections to terrestrial earthquakes. We can recognize that magnitude 6 earthquakes occurring within hours in the same region follows known patterns of stress transfer and aftershock sequences, without assuming solar weather influences. We can marvel at the timing of 3I Atlas's approach during solar maximum conditions, while understanding that this represents favorable observational circumstances rather than mystical synchronicity. We can celebrate the confluence of two bright comets during optimal viewing conditions, without concluding that cosmic forces orchestrated the alignment for human benefit. Media timing amplifies the everything at once sensation through concentrated reporting and social media amplification. When multiple dramatic events occur within days, news cycles and online discussions create echo chambers that reinforce perceptions of significance. The psychological impact of simultaneous coverage can make genuinely coincidental clustering feel more meaningful than statistical analysis would support. Archaeological and historical evidence reveals that humans have always sought cosmic significance in terrestrial events. Ancient civilizations interpreted comets as omens, eclipses as divine displeasure, and earthquake-comet coincidences as supernatural communications. These cultural patterns persist in modern contexts, where scientific knowledge coexists with deep psychological needs to find meaning in apparently random clustering. The challenge involves maintaining scientific rigor while acknowledging the emotional and aesthetic impact of remarkable convergences. We can appreciate the beauty of cosmic timing without abandoning critical thinking. We can feel wonder at the universe's occasional arrangements without assuming intentional design or hidden causation. Competing hypotheses deserve simultaneous consideration, provided we maintain clear distinctions between established science and speculative possibilities. The clustered but unrelated interpretation rests on solid physical foundations. Stellar physics explains novae. Plate tectonics explains earthquakes. Solar physics explains coronal mass ejections. And orbital mechanics explains comet approaches. Each phenomenon follows well-understood natural laws operating independently. The cosmic resonance interpretation ventures into more speculative territory, suggesting subtle connections between phenomena that mainstream science hasn't yet recognized or understood. This perspective doesn't require abandoning physics, but rather proposes that our current understanding may be incomplete in ways that could eventually reveal genuine correlations between apparently unrelated domains. Both perspectives can coexist intellectually, provided we maintain appropriate epistemological boundaries. Established science deserves primary consideration because it rests on extensive observational support and successful predictive capability. Speculative hypotheses deserve exploration, provided they remain clearly distinguished from proven knowledge and generate testable predictions. The autumn equinox season provides additional context that doesn't require exotic explanations. The Russell-McLaren effect creates geometric conditions that amplify space weather impacts during September and October, making this period statistically more likely to produce significant geomagnetic activity. Seasonal patterns in earthquake occurrence have been reported in some regions, though the mechanisms remain unclear and effects are typically subtle. Cultural archetypal frameworks offer narrative richness without requiring literal interpretation. Comets have symbolized change, upheaval, and cosmic communication across human cultures for millennia. Earthquakes represent the solid Earth, revealing its dynamic nature. Stellar explosions demonstrate the violent beauty of cosmic evolution. These archetypal associations provide powerful story elements that resonate with deep psychological patterns while remaining independent of physical causation. The invitation extends to viewers and readers. Hold competing hypotheses lightly, appreciating both scientific rigor and narrative wonder. We can enjoy the synchronistic feeling of cosmic events clustering without abandoning critical thinking. We can explore speculative connections while maintaining respect for established physics. We can celebrate the remarkable while acknowledging the probable. Perhaps the most honest approach involves embracing uncertainty while remaining open to discovery. Science advances through careful observation, hypothesis formation, and rigorous testing, rather than premature certainty about complex phenomena. The September-October convergence provides rich material for both scientific analysis and imaginative exploration, provided we maintain clear distinctions between what we observe, what we hypothesize, and what we actually know. As we dive deeper into these questions, one particular speculative connection deserves careful examination. The long-debated possibility that space weather might influence terrestrial seismic activity through mechanisms that remain poorly understood. Part 12. Space weather and earthquakes. The idea that solar storms might influence earthquake occurrence represents one of the most persistent and controversial hypotheses in Earth-space science. For decades, researchers have reported statistical correlations between various space weather phenomena and seismic activity. Yet no widely accepted physical mechanism explains how electromagnetic disturbances 93 million miles away could trigger sudden ruptures in Earth's crust. The most intriguing recent hypothesis comes from researcher Stephen Burns, who propose that drops in solar wind density following high-speed streams could create a kind of electromagnetic vacuum that might subtly alter crustal stress fields. According to this model, when dense, fast-moving solar wind suddenly gives way to the sparse, slow, background solar wind, the change in electromagnetic pressure on Earth's magnetosphere could theoretically propagate through complex coupling mechanisms to influence stress accumulation on fault systems. The physics would involve multiple steps, each introducing uncertainty and attenuation. First, solar wind density variations would alter the shape and pressure of Earth's magnetosphere, the magnetic bubble that shields us from most space weather effects. Changes in magnetospheric configuration could modify electric currents flowing through the ionosphere, Earth's electrically conductive upper atmosphere. These current variations might induce electromagnetic fields that propagate into Earth's crust, where they could theoretically influence piezoelectric stress in crystalline rock structures. Each step in this proposed causal chain involves effects measured in nanotesla magnetic field variations or microstrain stress changes, quantities thousands of times smaller than the stress changes needed to trigger earthquakes on fault systems that aren't already extremely close to failure. The theoretical coupling mechanisms exist, but their magnitudes appear insufficient to influence seismic activity under normal circumstances. What's actually established scientifically is the extensive literature of correlation claims, coupled with a conspicuous absence of causal demonstration. Studies dating back decades have reported statistical associations between solar flare activity and earthquake occurrence, geomagnetic storm intensity and seismic event clustering, and various space weather indices and regional earthquake catalogs. These correlations often appear statistically significant when first reported, but frequently fail to replicate when tested against different time periods, geographic regions, or earthquake catalogs. Publication bias complicates the literature significantly. Positive correlations between space weather and earthquakes are more likely to be submitted, accepted, and cited than null results that find no relationship. This creates an artificial impression of scientific consensus around connections that may not exist or may be far weaker than the published literature suggests. Meta-analyses attempting to synthesize multiple studies often find that effect sizes decrease as sample sizes increase and methodological rigor improves. The United States Geological Survey's official position, supported by international seismological organizations, maintains that no reliable correlation has been demonstrated between space weather and earthquake occurrence. This conclusion rests on extensive statistical analysis of global earthquake catalogs compared against comprehensive space weather databases spanning multiple solar cycles. When proper statistical controls are applied, correcting for multiple comparisons, temporal clustering, and selection bias, most reported correlations disappear or become statistically insignificant. However, some researchers continue exploring more subtle potential connections that might operate only under specific conditions. Atmospheric pressure variations associated with geomagnetic storms could theoretically alter stress on fault systems. Though these pressure changes typically measure less than 1 millibar, far smaller than normal weather-related pressure variations that show no clear correlation with seismic activity. Electromagnetic induction represents another proposed mechanism. Strong geomagnetic storms can induce electric currents in conductive materials, including underground water systems and mineral formations. These induced currents could theoretically alter electrochemical processes in fault zones, potentially affecting pore pressure or rock strength in ways that might influence earthquake timing. Again, the theoretical mechanisms exist, but the magnitudes appear insufficient to significantly impact well-established seismological processes. Gravitational effects offer a more promising avenue for space-Earth coupling, though not through electromagnetic mechanisms. Earth tides, caused by lunar and solar gravitational variations, demonstrably influence earthquake occurrence, with some studies suggesting slightly elevated seismic activity during periods of maximum tidal stress. These gravitational effects are well understood, measurable, and operate through established physical mechanisms that alter stress directly on fault systems. Could similar gravitational effects from other astronomical sources influence seismic activity? Planetary alignments, while popular in some alternative theories, produce gravitational effects orders of magnitude smaller than lunar tides. Even large planetary conjunctions generate tidal forces on Earth that are negligible compared to normal lunar-solar tidal variations. The challenge of testing space weather, earthquake connections lies in separating genuine physical relationships from statistical artifacts. Earthquake occurrence follows complex statistical patterns, including aftershock sequences, spatial clustering, and temporal correlations, that can easily generate spurious correlations with any time-varying external phenomenon. Space weather indices also show autocorrelation, periodicities, and clustering that could produce apparent relationships with seismic activity through pure coincidence. Proper testing requires pre-registered studies that specify hypotheses, time windows, geographic regions, and statistical methods before examining the data. Blind testing protocols, where researchers analyze earthquake catalogs without knowing the corresponding space weather conditions, could eliminate unconscious bias in data selection and analysis. Such rigorous approaches are rare in the literature, but essential for establishing genuine relationships. What would constitute compelling evidence for space weather earthquake connections? First, the proposed mechanism would need to demonstrate physical plausibility through laboratory experiments or theoretical modeling that shows how electromagnetic or particle effects could significantly alter stress fields in crystalline rock. Second, statistical relationships would need to show predictive skill beyond chance levels when tested prospectively against independent datasets. Third, any genuine connection would likely be conditional rather than universal, operating only in certain tectonic settings, stress states, or fault geometries. Universal correlations affecting all earthquake regions equally seem physically implausible, given the vast differences in local geology, stress fields, and fault mechanics across different seismic zones. The Venezuelan earthquake sequence occurred during a period of elevated space weather activity, providing another data point in the long-running correlation debate. However, individual coincidences prove nothing about systematic relationships. Venezuela sits in a tectonically active region where magnitude 6 earthquakes occur irregularly but predictably, based on plate boundary dynamics and regional stress accumulation patterns. If any genuine space weather earthquake connection exists, it would most likely be subtle and conditional rather than dramatic and universal. The effects might manifest only in fault systems that are already very close to failure, where tiny additional stress changes could advance rupture timing by hours, days, or weeks, rather than triggering earthquakes that wouldn't otherwise occur. Current seismological understanding suggests that earthquake timing depends primarily on local stress field evolution, fault zone properties, and stochastic processes operating within complex nonlinear systems. External influences, whether from space weather, atmospheric pressure, or other sources, likely play minimal roles compared to the dominant tectonic forces that accumulate stress over decades and release it suddenly during major ruptures. The most scientifically honest position acknowledges both the theoretical possibilities and the empirical limitations. Subtle electromagnetic or gravitational coupling between space weather and seismic activity cannot be ruled out entirely, but no convincing evidence demonstrates such connections operate with sufficient magnitude to influence earthquake occurrence detectably. Future research should focus on physics-first approaches that identify plausible mechanisms before searching for statistical correlations in observational data. For practical earthquake preparedness and risk assessment, space weather monitoring provides no useful information about seismic hazards. Building codes, emergency planning, and public safety measures should remain based on established seismological knowledge about fault systems, historical earthquake patterns, and probabilistic seismic hazard assessment, rather than space weather forecasts. As we explore these terrestrial connections, an even more speculative question arises. Could the energy from distant stellar explosions somehow influence Earth's climate or geological processes over longer timescales? Part 13. Novae and Climate. The idea that stellar explosions might influence Earth's climate operates across vastly different scales of energy, distance, and time than the space weather earthquake hypothesis we just explored. While nearby supernovae could theoretically affect our planet's atmosphere and climate over geological timescales, ordinary novae like V1935 Centauri and V7994 Sagittari are energetically far weaker and astronomically more distant, making any short-term terrestrial impact virtually impossible. Let's establish the scales involved with ruthless precision. A typical nova releases energy equivalent to our Sun's total output over roughly 10,000 years, approximately 1043 joules. This sounds enormous by human standards, capable of powering our entire civilization for billions of years at current consumption rates. However, this energy spreads spherically outward from the explosion site, diluting according to the inverse square law as it travels through interstellar space. V1935 Centauri likely sits several thousand light-years from Earth, meaning its explosion occurred millennia before human civilization developed writing, agriculture, or permanent settlements. By the time this ancient stellar violence reaches our solar system, the energy flux has diminished to levels comparable to bright starlight. Beautiful to observe, utterly negligible in terms of climate forcing or atmospheric chemistry. The energy that finally arrives at Earth from these September novae amounts to perhaps a few extra photons per square meter, less additional radiation than you'd receive from a flashlight held at arm's length. To put this in climate context, the total energy Earth receives from both novae combined over their entire brightening and decline phases would be insufficient to warm a single coffee cup by measurable amounts. Contrast this with nearby supernovae, which represent genuine candidates for astronomical climate influence over geological timescales. A supernova occurring within roughly 50 light-years of Earth could potentially deliver enough high-energy radiation to alter atmospheric chemistry significantly. The gamma rays and X-rays from such an explosion might destroy substantial portions of Earth's protective ozone layer, allowing increased ultraviolet radiation to reach the surface and potentially triggering mass extinction events. Some researchers have proposed connections between nearby supernovae and historical mass extinctions, though the evidence remains controversial and highly debated. The late Ordovician extinction, approximately 450 million years ago, coincides roughly with evidence for nearby supernova activity. But establishing definitive causal relationships across such vast timescales requires extraordinary evidence that currently doesn't exist. The proposed mechanisms for supernova climate influence involve complex atmospheric chemistry rather than simple thermal heating. High-energy photons from stellar explosions could dissociate nitrogen and oxygen molecules in Earth's upper atmosphere, creating nitrogen oxides that catalytically destroy ozone. Reduced ozone protection would allow more solar ultraviolet radiation to reach Earth's surface, potentially damaging ecosystems and altering global climate patterns through complex feedback mechanisms. Cosmic ray interactions provide another potential channel for stellar influence on terrestrial climate, though again at scales and timeframes far removed from the September nova events. Some theories propose that cosmic rays, high-energy particles accelerated by supernova shockwaves, might influence cloud formation in Earth's atmosphere by providing condensation nuclei for water droplets. Changes in cosmic ray flux could theoretically alter cloud cover and thus global climate, though experimental evidence for this mechanism remains limited and controversial. The September novae might contribute negligibly to cosmic ray backgrounds over astronomical timescales, but their immediate impact on Earth's cosmic ray environment would be utterly undetectable. The cosmic ray particles accelerated by V1935 Centauri and V7994 Sagittarii would require thousands of years to traverse interstellar space and reach our solar system, where they would be indistinguishable from the general background of galactic cosmic radiation. Media narratives often conflate different types of stellar explosions and their potential terrestrial impacts, creating confusion about actual versus imagined threats. Headlines suggesting that star explosions could affect Earth's climate typically fail to distinguish between nearby supernovae that might have measurable effects over geological time and distant novae that pose no realistic climate influence. This conflation feeds into broader patterns of astronomical sensationalism that prioritize dramatic storylines over scientific accuracy. The timing correlation between September's stellar explosions and terrestrial earthquakes provides fertile ground for pattern-seeking minds to construct causal narratives. But the energy scales involved make any direct connection physically implausible. The total energy that will ever reach Earth from both novae combined over their entire observable lifetimes equals less than 1 second of normal sunlight hitting our planet's surface. However, the scientific study of stellar explosions and climate remains a legitimate and fascinating field of research, provided it focuses on plausible mechanisms operating over appropriate timescales. The galaxy's supernova rate, roughly 1 to 3 explosions per century, means that Earth periodically encounters high-energy radiation from relatively nearby stellar explosions over millions of years of geological history. Isotopic evidence in geological formations sometimes preserves signatures of cosmic ray bombardment that might correlate with supernova activity. Iron-60, a radioactive isotope produced primarily in supernova explosions, has been detected in deep-sea ferromanganese crusts and ice cores, providing direct evidence that Earth occasionally experiences enhanced cosmic ray exposure from stellar sources. These isotopic signatures offer tantalizing glimpses of how stellar explosions might influence our planet over geological time, but they operate across scales of millions of years rather than days or months. The Iron-60 detection suggests that Earth experienced enhanced cosmic ray exposure roughly 2 to 3 million years ago, possibly coinciding with supernova activity in nearby stellar associations. The question of whether such enhanced cosmic ray exposure actually influenced terrestrial climate, atmospheric chemistry, or biological evolution remains open and actively researched. Some theories propose connections between cosmic ray flux variations and ice age cycles, though the mechanisms remain speculative and the evidence inconclusive. For the September 2025 novae, any climate influence remains purely academic and essentially zero. These distant stellar explosions will contribute no measurable energy to Earth's radiation budget, alter no atmospheric chemistry processes, and influence no climate variables detectably. They represent beautiful examples of stellar evolution and explosion physics occurring at safe astronomical distances, where we can observe and study them without experiencing any direct effects. The broader lesson involves maintaining perspective about astronomical scales and the difference between dramatic cosmic events and measurable terrestrial impacts. The universe regularly produces spectacular phenomena, stellar explosions, galactic collisions, black hole mergers, that generate enormous energies but remain too distant or too brief to influence Earth's climate system meaningfully. Our planet's climate responds primarily to solar radiation variations, atmospheric composition changes, ocean circulation patterns, and volcanic activity. Terrestrial and solar system processes operating over timescales from years to millennia. While exotic astronomical influences cannot be ruled out entirely over geological timescales, they remain negligible compared to the dominant forces shaping Earth's climate evolution. The psychological appeal of connecting distant stellar explosions to earthly phenomena reflects deep human needs to find meaning and pattern in apparently random events. These cognitive tendencies served our ancestors well in detecting genuine environmental correlations, but they can also lead us to perceive significance in the coincidental clustering of unrelated phenomena. As we have explored terrestrial connections to cosmic events, our attention returns to the interstellar visitor that may provide the most direct and immediate opportunity to study how our solar system interacts with matter formed around other stars. Part 14. Interstellar Visitors as Solar Probes. 3i Jochi 2025 Atlas represents far more than a curiosity from interstellar space. It is potentially the most sensitive natural probe we have ever had for studying how our sun interacts with material formed around other stars. While Oumuamua departed too quickly for detailed study, and Borisov remained relatively distant throughout its passage, this third interstellar visitor offers unprecedented opportunities to observe solar weather effects on matter that spent millions of years wandering between stellar systems. The geometry alone makes 3i Atlas extraordinary for heliospheric science. Unlike previous interstellar objects that followed highly inclined trajectories through the outer solar system, this visitor threads through the ecliptic plane, where solar wind density, magnetic field strength, and space weather activity reach their highest intensities. It is approaching during solar cycle 25 maximum conditions, when coronal mass ejection frequency peaks and solar magnetic field complexity reaches maximum chaos. Think of comets as natural magnetometers and plasma diagnostics floating through space. Their ion tails provide visible evidence of invisible magnetic field lines embedded in the solar wind. Changes in tail orientation, brightness, and morphology reveal information about solar wind speed, density, magnetic field direction, and the passage of shock waves or other disturbances. Professional space weather researchers have used solar system comets as remote sensors for decades, extracting quantitative measurements of space plasma conditions from telescopic observations. 3i Atlas potentially extends this capability to material with an entirely different formation history and chemical composition. While solar system comets condensed from the same primordial disk that formed our planets, this interstellar visitor carries volatiles created around a different star in a different stellar system, possibly billions of years ago. If coronal mass ejections alter its behavior, we are witnessing the first documented interaction between our sun's magnetic field and matter from another stellar neighborhood. The Mars flyby on October 3rd provides a unique observational geometry that ground-based telescopes cannot achieve. ESA's ExoMars Trace Gas Orbiter, TGO, and NASA's Mars Reconnaissance Orbiter, MRO, will observe 3i Atlas from positions approximately 0.19 astronomical units, AU away, roughly 28 million kilometers, offering viewing angles and resolution impossible from Earth-based observatories. MRO's high-resolution imaging science experiment, HiRISE camera, designed for high-resolution surface imaging, should achieve pixel scales of approximately 30 kilometers when pointed toward the interstellar visitor. While this resolution cannot reveal surface details of the nucleus, it may distinguish between a compact central condensation and extended coma structure. More importantly, simultaneous observations from Mars orbiters and Earth-based telescopes will provide parallax measurements that could constrain the visitor's size and activity level more precisely than single viewpoint observations. Spectroscopic capabilities from the Mars orbital platforms offer additional scientific value. The ExoMars TGO carries spectrometers designed to detect trace gases in the Martian atmosphere, instruments that could potentially characterize molecular emissions from 3I Atlas during closest approach. Detection of CN, CO, CO2, or other molecular species would provide direct evidence of the visitor's chemical composition and how solar heating liberates volatiles from interstellar ice. Ground-based observatories worldwide continue coordinating observation campaigns through the International Astronomical Union's Minor Planet Center and various professional astronomical organizations. The goal involves comprehensive multi-wavelength monitoring that tracks brightness changes, spectroscopic evolution, and morphological variations as 3I Atlas responds to varying solar wind conditions during its inbound journey. Amateur astronomers contribute crucial observations that professional observatories, focused on many different targets, cannot provide continuously. Visual magnitude estimates, CCD photometry, and imaging by dedicated amateur observers provide the temporal resolution needed to detect short-term variations that might correlate with specific space weather events. The precedent for dramatic CME comet interactions comes from extensive observations of solar system comets, most notably the stereo satellite documentation of Comet Encke's tail disconnection in 2007. That event demonstrated the violent reality of magnetic reconnection between solar plasma and cometary material, completely severing the ion tail in a process visible to spacecraft cameras and analyzable through plasma physics models. If similar disconnection events occur with 3I Atlas, they could provide unprecedented insights into how solar magnetic fields interact with interstellar material. The chemical composition differences between solar system and interstellar volatiles might produce different ionization patterns, magnetic coupling efficiencies, or reconnection dynamics that reveal fundamental aspects of plasma physics operating under conditions unavailable in terrestrial laboratories. The scientific questions extend beyond simple space weather interactions. 3I Atlas carries isotopic signatures from its birth stellar system that could reveal information about stellar nucleosynthesis processes, supernova enrichment patterns, and chemical evolution in other parts of the galaxy. Solar heating that liberates these ancient volatiles provides our first opportunity to analyze interstellar material spectroscopically at close range. The object's trajectory through multiple space weather environments, from the relatively quiet conditions of interstellar space to the intense activity near solar maximum, offers a natural experiment in how cosmic radiation and magnetic fields affect interstellar material over time. Observations might reveal whether millions of years of cosmic ray exposure have altered the visitor's chemical composition, physical structure, or volatile content compared to fresh solar system comets. Professional radio astronomy observations could detect molecular line emissions that reveal internal temperature structure, rotation rates, and outgassing patterns as solar heating penetrates into the nucleus. Very long baseline interferometry, VLBI techniques, might resolve structural details of the coma that indicate whether the nucleus is a single consolidated object or a loose collection of smaller components held together by weak gravitational attraction. The timing of 3I Atlas observations coincides with advances in space weather monitoring and modeling capabilities that were unavailable during previous interstellar visitor encounters. Real-time solar wind measurements from multiple spacecraft, sophisticated magneto-hydrodynamic models of CME propagation, and comprehensive ground-based monitoring networks provide context for interpreting visitor behavior changes that previous generations of astronomers could not achieve. 3I Atlas may also serve as a test case for planetary defense capabilities. Though it poses no collision threat to Earth, the object's trajectory, brightness evolution, and response to space weather provide opportunities to validate telescopic detection methods, orbital determination techniques, and characterization capabilities that would be essential if a potentially hazardous interstellar object ever approached our planet. The broader implications of interstellar visitor science extend to astrobiology and the search for life beyond Earth. If 3I Atlas carries organic compounds or other prebiotic materials from its birth stellar system, spectroscopic analysis could reveal whether the chemical building blocks of life are common throughout the galaxy. Such discoveries would have profound implications for understanding how biological complexity might emerge in other stellar systems. The visitor's extended observability through early 2026 ensures that scientific investigations can continue long after the initial Mars flyby excitement. Perihelion on October 29th and closest approach to Earth on December 19th provide multiple opportunities for detailed study as the object evolves under changing solar heating conditions. As we prepare for October's unprecedented observational opportunities, the convergence of events, interstellar visitor, solar maximum conditions, advanced monitoring capabilities, and coordinated international observation campaigns creates the potential for discoveries that could reshape our understanding of how stellar systems interact with interstellar space. The calendar pages ahead promise revelations that may answer fundamental questions about our place in the cosmic neighborhood. Part 15. Looking Forward. October and Beyond Circle. October 3rd, 20th, 21st, and 29th on your calendars. Mark December 19th in bold. These dates represent potential turning points in our understanding of interstellar visitors, space weather interactions, and the broader cosmic neighborhood that surrounds our solar system. What unfolds during these precise moments may answer questions that have puzzled astronomers since humanity first wondered about our place among the stars. October 3rd, Mars Encounter. October 3rd marks 3I Atlas's closest approach to Mars at 0.19 AU, roughly 28 million kilometers from the Red Planet. This represents the first time in recorded history that an interstellar visitor will pass within the orbit of Mars, orbiters specifically designed to study small bodies. NASA's ExoMars TGO and NASA's MRO have adjusted their observation schedules to capture this unprecedented encounter between technology and interstellar matter. The viewing geometry offers advantages impossible to achieve from Earth-based observatories. Mars orbiters will observe 3I Atlas from positions that provide different viewing angles, potentially resolving ambiguities about the visitor's size, shape, and activity level that single viewpoint observations cannot address. Simultaneous observations from Mars and Earth could provide parallax measurements that constrain distance and physical dimensions more precisely than previous interstellar visitor encounters allowed. Harvard astronomer R.V. Lowe's description of the encounter as a blind date with Mars captures both the excitement and uncertainty surrounding these observations. MRO's high-rise camera should achieve resolution scales of approximately 30 kilometers per pixel when pointed toward the interstellar visitor. Insufficient to reveal surface details, this Resolution is potentially capable of distinguishing between a compact nucleus and extended coma structure. The scientific expectations must remain realistic to avoid disappointment when initial results become available. Interstellar visitors appear as point sources even to the most powerful telescopes at distances exceeding 1 astronomical unit. The most likely outcomes involve improved constraints on size, brightness evolution, and spectroscopic composition rather than dramatically resolved imagery of exotic structures or unexpected phenomena. October 20th and 21st, Comet Swan. October 20th and 21st promise a different type of celestial spectacle as Comet C2025R2, Swan, reaches its closest approach to Earth at approximately 0.26 to 0.27 AU. The timing coincides perfectly with new moon conditions that eliminate lunar interference and the annual Orionid meteor shower peak, creating optimal dark sky conditions for comet observation. Current brightness predictions suggest Comet Swan could reach magnitude 4 to 6 during closest approach. Bright enough for naked eye visibility under dark skies and excellent viewing through binoculars or small telescopes. However, comet brightness predictions carry enormous uncertainty, especially for newly discovered long-period comets making their first recorded approach to the inner solar system. Swan could exceed expectations dramatically or disappoint observers if it fails to develop the spectacular tail structures that make comets visually memorable. The confluence of multiple celestial events during late October creates unprecedented opportunities for comparative observations. Skywatchers could potentially observe an interstellar visitor, a bright solar system comet, multiple meteors per hour from the Orionid shower, and continuing space weather effects from solar cycle 25 maximum, all during the same optimal viewing sessions under dark moon conditions. October 29th, perihelion for Atlas. October 29th represents 3I Atlas's moment of maximum solar heating as it reaches perihelion at approximately 1.36 AU from the Sun. This closest approach to our star will subject the interstellar visitor to thermal conditions that may liberate volatile compounds locked in its nucleus for millions of years during its journey through interstellar space. Perihelion observations could reveal whether 3I Atlas follows typical comet evolution patterns or displays unique characteristics reflecting its interstellar origins. Solar heating may produce dramatic brightness increases, spectacular tail development, or fragmentation events that distinguish interstellar visitors from solar system comets formed under different conditions. The perihelion distance keeps 3I Atlas outside Earth's orbit, farther from the Sun than our planet, but close enough for detailed ground-based observations throughout late 2025. Professional observatories worldwide have coordinated observation campaigns to monitor brightness changes, spectroscopic, evolution, and morphological variations as the visitor responds to peak solar heating. December 19th, Earth approach. December 19th marks 3I Atlas's closest approach to Earth at roughly 1.8 AU, approximately 270 million kilometers. For comparison, this distance is closer than Mars at its most distant point from Earth, providing excellent viewing conditions for both professional observatories and amateur astronomers with modest telescopes throughout the winter months. The extended observability of 3I Atlas through early 2026 ensures that scientific investigations can continue long after the initial excitement of the Mars flyby and perihelion passage. Unlike Oumuamua, which departed the inner solar system too quickly for comprehensive study, this interstellar visitor offers months of detailed observation opportunities as it evolves under changing solar heating conditions and space weather influences. Managing expectations and future analysis. What to expect versus what constitutes hype requires careful calibration of public expectations. Comets and interstellar visitors are notoriously unpredictable objects that can exceed expectations dramatically or disappoint observers who anticipate spectacular visual displays. The most likely scenarios involve gradual brightness changes, subtle spectroscopic evolution, and morphological variations detectable through telescopic observations, rather than dramatic naked-eye phenomena visible to casual observers. Professional imaging may reveal structural details of coma development, tail formation, and response to solar wind variations. But these discoveries will likely manifest as scientific data rather than visually spectacular displays. The most significant results may emerge from spectroscopic analysis that reveals chemical composition, isotopic ratios, and volatile content, rather than dramatic visual transformations that capture media attention. Space weather monitoring continues at elevated intensity as Solar Cycle 25 maintains peak activity levels through late 2025 and early 2026. The Russell-McFerrin effect during the autumn equinox season enhances the probability of significant geomagnetic activity, potentially producing spectacular auroral displays and space weather impacts on technological systems. NOAA's Space Weather Prediction Center maintains continuous monitoring of solar activity through multiple satellite systems and ground-based observatories. The Enlil model continues tracking coronal mass ejection propagation through the heliosphere, providing forecasts of when solar storms might interact with Earth's magnetosphere, Mars orbiters, and the trajectory of 3I Atlas. Aurora photographers and space weather enthusiasts should monitor SWPC alerts for G-scale geomagnetic storms, S-scale solar radiation events, and R-scale radio blackouts that could produce visible auroral activity at lower latitudes than typical quiet conditions allow. The combination of solar maximum conditions and favorable equinox geometry creates optimal prospects for dramatic space weather displays throughout October and November. Earthquake monitoring in Venezuela continues as aftershock sequences evolve, following the magnitude 6.2 and 6.3 main shocks of late September. Seismological organizations maintain continuous surveillance of regional seismic activity, though no reliable methods exist for predicting whether larger events might occur in the same region over short timescales. The complex tectonics of the Caribbean-South American plate boundary ensure that this region will continue generating earthquakes irregularly, but inevitably over geological time. Building codes, emergency preparedness systems, and public safety measures should remain based on established seismological knowledge rather than speculative connections to space weather or astronomical events. NOVA monitoring continues for both V1935 Centauri and V7994 Sagittari. As these stellar explosions evolve through their characteristic brightness decline phases, professional and amateur astronomers worldwide contribute photometry and spectroscopic observations that reveal how nova physics unfolds over timescales of months to years following the initial thermonuclear explosion. The American Association of Variable Star Observers coordinates these monitoring efforts through standardized protocols that allow meaningful comparison of observations from different observers using various equipment. The high-energy signatures detected by Fermi and Swift satellites continue providing insights into particle acceleration processes operating in nova shockwaves. Dust formation episodes may occur in either nova during the coming months, producing temporary brightness declines as newly formed microscopic particles absorb and scatter the star's light. These dust dip events, if they occur, would provide additional information about nova ejecta composition and the physical conditions in expanding stellar explosion remnants. Conclusion: coincidence or connection? The story we will tell about October and beyond depends critically on separating observational results from speculative interpretation. Each phenomenon, interstellar visitor behavior, space weather activity, seismic monitoring, and nova evolution, follows established physical laws that operate independently of the apparent temporal clustering that captured our attention during late September. Yet the convergence itself deserves documentation and analysis as a remarkable example of how the universe occasionally arranges dramatic events across multiple domains during compressed time intervals. Whether this clustering represents pure coincidence, subtle physical connections we do not yet understand, or simply the inevitable result of living in a dynamic cosmos remains an open question that observations may help resolve. The call to action for the public involves enjoying these celestial events safely, while maintaining realistic expectations and consulting authoritative data sources rather than sensationalized media reports or unsubstantiated rumors. NASA, ESA, the Minor Planet Center, the USGS, and NOAA's Space Weather Prediction Center provide reliable, continuously updated information about ongoing developments. Amateur participation in these observations offers meaningful opportunities to contribute to scientific understanding while experiencing the wonder of cosmic phenomena firsthand. Comet photography, visual magnitude estimates, aurora observation, and earthquake reporting through established networks allow citizen scientists to participate directly in documenting this remarkable period of cosmic activity. The speculative question that shadows all these observations involves whether the temporal clustering represents something more than statistical coincidence. If this convergence feels strange, and it does to many observers, perhaps that is because our normally separated timescales, stellar evolution, geological processes, solar activity, and interstellar visitor encounters have briefly overlapped in ways that rarely occur within human lifespans. The promise extends beyond October's immediate observations to follow-up analysis once Mars orbiter data, perihelion spectroscopy, and extended monitoring results become available. We will analyze what actually arrived rather than forecasting what might occur, maintaining the distinction between observation and interpretation that forms the foundation of reliable scientific investigation. The final assessment of this remarkable convergence may require years of careful analysis to separate genuine physical relationships from coincidental clustering, established science from speculative connection, and meaningful pattern from psychological projection. What remains certain is that we are witnessing a confluence of cosmic events that spans scales from stellar explosions to terrestrial earthquakes to interstellar visitor encounters. A reminder that we inhabit a universe far more dynamic and interconnected than our daily experience typically reveals. In the end, perhaps the real story isn't whether these events are cosmically connected, but that we live during the first generation in human history, capable of detecting, monitoring, and studying such convergences across multiple domains of space and time. A perspective that would have been impossible for any previous civilization in Earth's history.